Hello students, welcome to physics class. Today we discuss moving coil galvanometer. We know that a galvanometer is a device to detect current in a circuit. The principle of moving coil galvanometer is that a current carrying coil placed in a magnetic field experiences a current dependent torque which tends to rotate the coil and produce an angular deflection. This principle we already discussed. That is the torque experience for a coil, current carrying coil in a magnetic field. So that's the working principle of a moving coil galvanometer. A current carrying coil placed in a magnetic field experience a current dependent torque which tends to rotate the coil and provide an angular deflection. Now see the construction of a moving coil galvanometer. A moving coil galvanometer consists of a coil that is usually copper wire wound on a rectangular aluminum frame. Usually this copper wire consists of many turns which wound in a rectangular frame, aluminum frame. And inside this rectangular aluminum frame, we are inserting a cylindrical soft iron core. The function of this cylindrical soft iron core inside this rectangular frame to make the field as radial, to produce a radial magnetic field. A radial magnetic field is just a magnetic field which is always parallel to the plane of this coil. If the coil is turned under the torque, always the magnetic field is acting parallel to the plane of this coil. The magnetic field lines look like as a radius of a circle. That's why we call it a radial magnetic field. The importance of this radial magnetic field is that always it is parallel to the plane of the coil. If the coil is turned at any angle, the magnetic field is parallel to the plane of this coil and is getting a torque which is independent of the angle. The torque acting on the coil is maximum at any angle. The torque is independent of the angle if the field is radial. So by using a horseshoe magnet and inserting a soft iron core inside this rectangular frame, we produce a radial magnetic field in a moving coil galvanometer. So this is another part of a moving coil galvanometer. We have a horseshoe magnet to produce a radial magnetic field with the soft iron cylinder. And a spring is connected to the cylinder to control the rotation of this frame. Or to control the rotation of this coil, a spring is connected to the coil like this. When the spring is rotated or if the coil is rotated, the spring controls the rotation of this coil. And one pointer is connected to the cylinder to show the reading on a scale. Here we have a scale. The pointer shows the reading on the scale. The horseshoe magnet, that is the permanent magnet, and the cylindrical soft iron core which is inserted the rectangular frame make a radial magnetic field. So that is the construction of a moving coil galvanometer. Now see the working of this moving coil galvanometer. This is our rectangular frame PQRS which is inside a radial magnetic field. We know that what is a radial magnetic field? A radial magnetic field always parallel to the plane of this coil. The angle between normal and magnetic field at any alignment of this coil is 90 degree. So you can write the expression for the torque acting on this coil is torque is equal to NABI sin theta. But theta is equal to 90 degree as the field is radial. So the torque acting on the coil can be written as NABI. And you know that this torque is a current dependent torque. The torque is a current dependent torque. Torque is equal to NABI. Torque is directly proportional to current. When current increases, torque also increases. So As the torque acting on this coil, the coil start rotating. The coil start rotating under the action of this torque. But you know that this coil and rectangular frame is connected to a spring. A hair-like spring is connected to the rectangular frame to restrict the motion of this coil. So when the coil is turned, an opposing torque given by the spring which oppose the turning of this coil. So an opposing torque is producing. So let us say the torque to deflect the coil through an angle alpha. If the coil is turned through an angle alpha, a restoring torque is set up in the coil due to elasticity of this spring. Due to the elasticity of the spring, a restoring torque is produced on the coil, and this restoring torque, we can say it is depends on the angle through which it turns. If it turns through an angle alpha, the restoring torque is directly proportional to alpha. Or the restoring torque produced on this coil is equal to K into alpha. K is the torsional constant of the spring. K is the torsional constant of the spring. Or torsional constant means the torque produced when it turned through an angle, unit angle. The torsional constant means the torque produced on the coil when the coil is turned through a unit angle. So that is the torsional constant of the spring. When the spring is turned through a unit angle, what is the torque acting on it? Torsional constant. So into alpha, you getting the total torque. The restoring torque is equal to K into alpha. At equilibrium means the restoring torque and the deflecting torque are same. So at equilibrium, the pointer stops at a particular reading on the pointer. So we can say the restoring torque is equal to deflecting torque. So K into alpha is equal to NABI. K into alpha is equal to NABI. The restoring torque is equal to deflecting torque, NABI. Or alpha is equal to rearrange this equation. Alpha is equal to NABI by K. NABI by K. Or alpha is proportional to I. The deflection on this galvanometer is proportional to current passing through this coil. Alpha is directly proportional to I. Or we can write I is equal to, rearrange this equation, I is equal to K by NAB into alpha. I is equal to K by NAB into alpha. See, K is a constant, that's torsional constant of the spring. N, the number of turns in this coil. A, area cross section of this coil. B is the strength of magnetic field. Okay, so I is equal to one constant into alpha. I is equal to one constant into alpha. That constant can be written as G into alpha. Where G is equal to what? K by NAB. G is known as galvanometer constant. G is known as galvanometer constant. And G is equal to, we can write G equal to I by alpha. G equal to I by alpha, galvanometer constant, which is also known as figure of merit of galvanometer. G is also known as what? The figure of merit of galvanometer. The figure of merit of galvanometer is nothing but is the current which produces a deflection of one scale division in the galvanometer. It is the current which produces one scale deflection in the galvanometer. What is figure of merit? The current which produces a deflection of one scale division in the galvanometer. Figure of merit G is equal to I by alpha. I by alpha, which is equal to K by NBA. What is N, A and B? N is the number of turns in this coil. A, area of this coil. B is the strength of magnetic field. In the torque also we can say N is the number of turns. A, area of the coil. B is the strength of magnetic field. Strength of radial magnetic field. So that is the figure of merit of a galvanometer, which is a constant, and it is the deflection, or it is the current which produces a unit deflection in the galvanometer, and its unit can be ampere per division. Ampere per division, that is the SI unit of figure of merit. Now let us see, when will you say the galvanometer is sensitive, or what is the sensitivity of a galvanometer? A galvanometer is said to be sensitive if it shows a large scale deflection even when a small current is passed through it or small voltage is applied across it. That's the sensitivity of a galvanometer. If a galvanometer is sensitive, it shows a large scale deflection even when a small current is passing through the coil, or even it is connected to a small voltage, it shows a large scale deflection. Then the galvanometer is sensitive. And we can say the two types of sensitivity of a galvanometer. One is its current sensitivity and other is its voltage sensitivity. Let's see what is current sensitivity and what are the factors affecting the current sensitivity. It is defined as the deflection produced in the galvanometer when a unit current flows through it. It is the deflection in the galvanometer for a unit current. IS is equal to current sensitivity. IS is equal to alpha by I. Alpha is the deflection and I is the current. Alpha by I is the current or the deflection for unit current. So can be write as NAB by K. And voltage sensitivity. Voltage sensitivity. It is defined as the deflection produced in the galvanometer when a unit potential difference is applied across it. It is defined as the deflection produced in the galvanometer when a unit potential difference applied across it. And voltage sensitivity is equal to alpha by P. But V is equal to, we know V equal to I into R. V is equal to I into R. So we can simply write as the voltage sensitivity is equal to alpha by I into R. Alpha by I into R. Voltage sensitivity is equal to alpha divided by I into R. That's why NAB by K into R. NAB by K. This is equal to current sensitivity. Current sensitivity by R. Current sensitivity by R. That is the voltage sensitivity. What is R? The resistance of our coil. R is the resistance of our coil. So the factors affecting the current sensitivity and the voltage sensitivity are: one is, in case of current sensitivity, it depends on the number of turns. Number of turns in the coil. When the number of turns increases, current sensitivity increases. The second, area of cross section. Area of the coil. When area increases, current sensitivity increases. The third one, the strength of magnetic field. The strength of magnetic field and current sensitivity are directly proportional. And third one is inversely proportional to K. What is K? The torsional constant. So these are the factors which affecting the current sensitivity of a galvanometer. But if you are increasing the number of turns and area cross section, the galvanometer become too bulky. So in order to avoid that one, usually what you are doing is we are reducing the value of K. If you are reducing the K, that is torsional constant of the spring or suspending wire, we can increase the current sensitivity. Now what about the voltage sensitivity? Voltage sensitivity is actually independent of the number of turns. Why? Because when the number of turns increases, the length of the coil increases. When length of the coil increases, the resistance of the coil increases. So when N increases, correspondingly R also increases, keeping N by R as a constant. So we can say voltage sensitivity cannot increase by increasing the number of turns. When number of turns increases, R also increases. So N by R will be a constant. So the voltage sensitivity cannot increase by increasing the number of turns. And other factors are, one is area cross section. When area cross section increases, voltage sensitivity can be increases. When B increases, the strength of magnetic field increases, the voltage sensitivity increases. And the voltage sensitivity is inversely proportional to K, the torsional constant of the spring. When K increases, the voltage sensitivity decreases. So we can increase the voltage sensitivity either by increasing the area cross section or increasing the strength of magnetic field, or decreasing the value of the K, the torsional constant. So that's why if you are decreasing the torsional constant, usually to decrease this torsional constant, we are using a particular type of spring that we calling as phosphor bronze. The material for making that spring, usually we are using phosphor bronze. It's an alloy. If you are using this phosphor bronze for that making that spring, the K will be minimum, and we can increase the sensitivity of our galvanometer. So these are the factors. Generally, we can say sensitivity of a galvanometer depends on the number of turns of the coil, is directly proportional to the number of turns of the coil, directly proportional to the strength of magnetic field, and directly proportional to the area of the coil, area of the coil, and it's inversely proportional to the torsional constant of the spring. These are the factors which affecting the sensitivity of a galvanometer. That's all today. Thank you.